China says it hit 1 nanometer with a 99.77% yield. No warm-up, no polite preamble. If that's accurate, it doesn't nudge Moore's law, it snaps it clean in half. 1 nanometer means your patterning features just a few atoms across. At that scale, electrons don't politely follow copper lanes, they tunnel through barriers like ghosts through drywall. And the machines the rest of the world depends on to get anywhere near 2 to 3 nanometers, ASML's EUV scanners, are largely blocked from Chinese fabs, so the question lands hard. How did they pull this off, or did they? 1 nanometer can wear multiple masks. It could be a legitimate lab-grade proof of concept, tiny sample size, pristine conditions, pristine numbers. It could be a marketing label slapped on a single feature dimension, gate length, metal pitch, rather than a full, production-proven process node. Or it could be deliberate psychological warfare. Toss out an audacious figure to spook rivals, steady domestic investors, and signal that tech sanctions aren't slowing the march towards self-reliance. Each interpretation points to a different outcome for the chip industry, export controls, and the AI arms race. To decide which mask fits, you have to start with physics. A nanometer is a billionth of a meter. A DNA strand is roughly 2 to 2.5 nanometers wide. At 1 nanometer, you aren't shrinking transistors so much as negotiating with quantum mechanics. Gate dielectrics only a few atoms thick start leaking badly, variability spikes, and heat budgets collapse. FinFETs, the backbone of the 7 nanometers per 5 nanometers era, gradually give way to gate-all-around and nanosheet architectures precisely because short-channel effects get vicious as dimensions drop. That's why TSMC and Samsung sit at 3 nanometers today, aiming for 2 nanometers in 2025 to 2026, and why every step has required EUV lithography, exotic high-K dielectrics, and mind-bendingly complex patterning. Drop that context into China's situation, and the claim gets even spicier. Without EUV, one brute force path is to drive deep ultraviolet lithography into extreme multi-patterning. Double, quadruple, even octuple exposures, stacking patterns like a microscopic Jenga tower. It's technically feasible, but brutal. Throughput dives, alignment tolerances become hair-trigger sensitive, and costs go orbital. A cleaner but tougher route involves new materials. 2D semiconductors like graphene or molybdenum disulfide can form channels just 1 atom thick, helping tame leakage and short-channel problems. Couple those with GAA transistors, and you sketch a credible path below 2 nanometers, on paper. The snag is scale. Growing uniform 2D films across a 300 mm wafer, forming low-resistance contacts, and integrating everything into a production flow with 6 sigma repeatability is a nightmare no one has fully solved. Yes, AI-assisted EDA can optimize layouts, predict defects, and tweak process windows, but software can't conjure missing photons or replace a tool you're banned from buying. It optimizes the sandbox. It doesn't remove the walls. Still, healthy skepticism isn't the same as dismissal. Even if the 1 nanometer bombshell is inflated, China's semiconductor climb is real, steady, and broad. SMIC reportedly taping out 5 nm-class logic with only DUV shows what ingenuity under constraint can do. Meanwhile, China's command over mature nodes, 28 nanometers, 14 nanometers, 12 nanometers, feeds colossal markets: autos, industrial control, power management ICs, ubiquitous IoT. These chips don't headline conferences, but they prop up supply chains everywhere. And the investment isn't token. Hundreds of billions of dollars are pouring into fabs, EDA software, lithography and metrology startups, materials science, and advanced packaging. It's less a single moonshot and more a continental shift toward self-sufficiency. Fill every rung, own every link from design tools to photoresists. Now play the what-if game in both directions. If the 1 nanometer claim is genuine and scalable, US-led export controls aimed at freezing China at 14 nanometers or 7 nanometers go obsolete overnight. Any national security calculus around AI leadership, cryptography, hypersonic weapons, and surveillance shifts instantly. Data centers could hit new performance per watt ceilings, easing the AI energy binge. Autonomous vehicles, drones, and battlefield systems would process faster with less power. The ripple could upend not just geopolitics but global tech economics. Flip it. If the claim is mostly smoke, the damage isn't trivial either. Domestic capital could be misallocated chasing a mirage, credibility with global partners erodes, and policymakers might coast on a false sense of achievement. Either way, uncertainty spikes, And supply chains allergic to uncertainty now have another itch they can't scratch. Part of what makes this episode algorithmically irresistible is the narrative collision. Textbooks and ITRS roadmaps say, not yet. A sanctioned nation says already. Viewers are forced into detective mode. You can't just absorb 99.77% yield at 1 nanometer and move on. You want wafer maps, TM cross-sections, ID VG curves, patent filings, and teardown reports from outfits like Tech Insights or Yole. You want an AR-14 preprint with reproducible data or a peer-reviewed paper from a reputable lab. Because none of that has surfaced publicly at scale, speculation fills the vacuum. And speculation is jet fuel for YouTube. Controversy sparks comments, comments extend watch time, and watch time feeds recommendations. The platform rewards unresolved questions with high stakes. If you're trying to separate signal from noise without a clean room in your garage, follow 3 breadcrumbs. First, equipment. True 1 nanometer implies either clandestine EUV class replication, a breakthrough DUV workaround, or a new optical trick. Watch for surges in domestic lithography announcements, high-NA optics patents, resist chemistry breakthroughs, or unusual orders for precision metrology tools. Second, materials. A real shift to 2D channels or novel high-K dielectrics leaves trails. Cross-institution collaborations, licensing deals, reproducible wafer-scale demonstrations with credible mobility and contact resistance numbers. Third, product. Eventually, chips ship. If a server CPU, defense-grade ASIC, or consumer SoC allegedly built on a 1 nanometer line hits the market, someone will delit it, measure gate lengths, and publish. Silicon can hide behind slogans. It can't hide under an electron microscope. There's also a plausible middle win scenario. Imagine a Chinese fab builds a 1 nanometer gate length transistor array on a test vehicle, hits near perfect yield on that narrow slice, and broadcasts the peak number to galvanize funding and policy support. Is that deceit? In an industry where TSMC's N3 isn't literally 3 nanometers and Intel's 20A/18A roadmaps lean into poetic angstrom branding, it looks more like aggressive framing. The difference now is that every framing exercise is filtered through geopolitics. Claims become national statements, not just engineering milestones. Zoom back to us, developers, creators, consumers. If a truly manufacturable 1 nanometer process with high yield goes mainstream, your phone could run large AI models locally, no cloud hop, faster responses, better privacy. AR/VR headsets could offload compute into wafer-thin modules, making immersive worlds less battery-hungry. Data centers could slash power bills, slowing the carbon climb of AI inference. EVs could crunch sensor data faster and safer. Medical implants, edge sensors, and brain-computer interfaces would level up inside tighter power envelopes. But if this is puffery, the next 5 years still won't be dull. 2 NM-class nodes, chiplets, 3D stacking, backside power delivery, and smarter software will keep pushing performance even without a 1 nanometer badge. There's a darker flip side. Compute this dense and cheap, if locked behind opaque walls, magnifies concerns about surveillance, cyber offense, and autonomous weapons. As processing power becomes ubiquitous, both utopian and dystopian uses accelerate. Tech sovereignty narratives collide with ethical debates. Transparency, or strategic opacity, becomes a weapon. The less outsiders know about what your chips can do, the harder it is to build norms, defenses, or countermeasures. In the end, the China 1 nanometer saga acts like a prism. Tilt it and you see engineers wrestling quantum gremlins. Tilt again and marketers stretching nanometer until it snaps. Tilt once more and strategists gaming out sanctions, alliances, and investment flows with spreadsheets and scenarios. What's beyond dispute is that China is deadly serious about chip independence, investing money, talent, and political will into every layer of the stack. And the West isn't idle. Intel's angstrom push, TSMC's high-NA EUV bets, Samsung's GAA ramp, all show an industry still ready to burn billions to wring another node from stubborn physics. Maybe the real headline isn't China broke physics or China lied, but progress just got harder to measure. In that ambiguity, narratives can matter as much as nanometers. Atoms obey quantum rules, markets, media, and ministries obey belief. If enough stakeholders accept that China has 1 nanometer with near-perfect yield, policies shift, capital flows, competitors pivot, even if the atomic reality is blurrier. Conversely, if skepticism calcifies into automatic dismissal, Genuine breakthroughs risk being buried under geopolitics and cynicism.